In this video, I'll walk through how to create a load displacement curve for a open hole tension composite coupon. So on the screen here I have a open hole composite coupon that I plan on fixing on the left hand side and applying a load to the right hand side. Now what I want to do to make this creation of a load displacement curve easier is I want to tie a single node's displacement in the axial or x direction to the displacement of all the other nodes on one end. And what this will allow me to do is apply a displacement or a force to a single node, but that force is then transmitted to all the other nodes along that same coupon edge via this equation that ties the axial displacement between the load node and all of the follower nodes together. So to do this, I'll create what's called an equation constraint, and the first part of this is to create two node sets. One node set will be an individual node on this loading end, and the other node set will be every other node excluding that one node that I'll refer to as the load node. So I'll go ahead and create these two sets. So again, I'll choose just one node. It can be any node, but I'll just choose one node to be my load node. And then I can choose every other node except for the node I've already defined as my load node to be an additional node set. And I got rid of this node by holding down the control button while clicking on it to remove that node from this node set. So now that my two node sets are created, I'll go ahead and create my equation constraint. Now I'm in the interaction module, so I can click on my create constraint button and I can create an equation constraint. Now the way an equation constraint works is explained by clicking on this tip button, and the idea to focus on is that what I'm going to be doing is tying a degree of freedom for one set to a degree of freedom of another set. So what I'm going to be doing is setting my degree of freedom 1, the x direction degree of freedom for my load node, equal to the x direction displacement degree of freedom 1 for my follower nodes. So the way the equation constraint works is that all terms have to be on the left hand side of the equation and equate to 0. So I'm going to have my load node for my degree of freedom 1 minus my follower node's degree of freedom 1. It's going to be equivalent to 0. So the way I'm setting that up will be I'll assign a coefficient of 1 and -1 to my load node and follower nodes. And an important tip here is, and I've already reversed these, is that the first set in the equation can contain one or more nodes, but each additional set has to contain only one node. So my first set is my follower nodes that are multiple nodes, and my second set is my load node that is just a single node. It doesn't matter which coefficient I assign to which set. And then I just have to specify that I'm going to be tying the degree of freedom in the one direction, the axial x direction. So now I have a constraint equation on this entire load end of my composite coupon. Now in the load module, I can create a boundary condition or a load to apply to my individual load node that will then be transferred to the entire rest of the composite coupon. And I'll explain why that's important when we start to query the field output variables to create the load displacement curve. But for this example, I'm going to go ahead and create a displacement controlled loading. I'll apply that load to my load node, and I'll give it a displacement of 5. So now after I run this analysis, I can look at the results for my coupon. And what I've plotted on the screen here is the reaction force in the axial direction, the RF1 field output variable. And you can see that because I was applying a displacement load to my single load node, the majority of the reaction force is concentrated at this single node. The best way to think about a reaction force is the force necessary to cause a certain displacement to be enacted on a node. So when I applied a displacement of 5 to my load node, this reaction force variable calculates what force would be needed to be applied to that node to induce a displacement of 5. So what I want to do now is create a set of XY data for a field output variable at a unique nodal location. And the output variable I want to create XY data for is RF1. So remember that I applied a displacement controlled loading to this coupon, so it's a reaction force that I want to plot because it's a reaction force that will vary in a nonlinear analysis. If I had applied a concentrated force to my coupon, I would want to create XY data for the axial displacement of my composite coupon because the displacement would vary as the loading steadily increased. So I want to collect data for the reaction force in the one direction, and I want to choose my load node set as the point at which I'm collecting the XY data. So once I have my XY data, I can plot it just by right-clicking and click on plot. And what you can see here is that because I have progressive failure turned on and my composite material is allowed to fail and then the overall coupon stiffness is degraded, you can see that by plotting the reaction force, you can see when material failure starts to create nonlinearity in the overall load displacement response of this coupon, and then you can find the point where the ultimate load eventually occurs in the composite coupon. And those are really the only steps involved in creating a load displacement curve to view in Abaqus. There is one additional thing we can do, and that's exporting this data into an Excel spreadsheet. So the first process to do that is to rename our composite XY data. And then we can select Report, XY, we can select our LD curve data, and we can export a report file. I'll name this also just LD curve. And then in Excel, I can read this LD curve data into my Excel spreadsheet. And then when I read it in, I can separate the data by spacing. So I have 2 columns. And now I can simply take this data in Excel and plot it as a scatter plot, just as I would for any other type of Excel data.